So in stoichiometry, it's really just a fancy term of finding the amounts of reactants or products being made or used. Yeah, it's very simple. All right, so what can we do with it? Well, if we are provided a generic equation like reactant A plus reactant B yields product 1 and product 2, then knowing the balanced chemical equation, if we're given one item, we know the amount of another. Like if we're given the amount of reactant A or B, it doesn't matter, then we could find the amount of reactant B or A that's needed to react with it. We'd also be, if we were given the amount of reactant A or B, we'd also, from the balanced chemical equation, be able to tell you the amount of product 1 or product 2 that would be made. And finally, if we know the amount of product 1 or product 2 that we want to produce or that we have produced, then we can find the amount of the reactants of either one that we would need to use to do that. Right? So this balanced chemical equation is very, very powerful and allows us to do a lot of this prediction. And we can then use that theoretical prediction to compare to what we see in the lab space and determine percent yields or efficiency of the reaction or whatever. All right, so it's almost like a governing equation to building something. So since we're like near the end of the day and we're all kind of hungry, we'll look at a Big Mac. How about that? Or a Krabby Patty. I don't know, whatever. All right, so we'll simplify it a little bit. All right, 2 patties with 3 pieces of bread yields 1 Big Mac. All right, so this is all rice. This is a governing reaction. This is a balanced chemical equation for building a Big Mac. Right. So if we happen to have 4 patties, how much bread do we need in order to complete the process? Well, we would need 6 pieces of bread to make 2 Big Macs, right? Very simple. What if we had an excess amount of patties, but only 18 pieces of bread? We'd be able to make... No, we know it better than that. 6. Yeah, we made 6 Big Macs. Yep. All right, so if we had produced 25 Big Macs, then from this balanced chemical equation or recipe for a Big Mac, we would be able to tell you exactly how many patties and pieces of bread we need. Yeah, we need to have 50 patties and 75 pieces of bread. Right? So once we have this balanced chemical equation figured out, it kind of sets up anything else we want to throw at it as far as like how much do we need to how much we make, or how much have we made to how much do we need. All right, it's a very simplified idea, but I mean it really does match up nicely with what a balanced chemical equation can do for you. We have a new enhanced stoichiometry island diagram. And simply what we've done is taken one mole island diagram and connected it to another using the coefficients from the balanced chemical equation. So if we wanted to know, like if we knew a starting amount of substance A and we had a balanced chemical equation, then it's going to be the coefficients that link us from one substance in that reaction to another. It could be from one reactant to one product. It could be a reactant to another reactant. Like our number 8 example that we had done on the board, where we have 3 parts sodium hydroxide plus our phosphoric acid yielding 1 part sodium phosphate and 3 parts water. We can use these coefficients then as the connecting piece from moles of one to moles of another. Right? If we had 3 moles of sodium hydroxide, then for us to use it all to completion, we would need 1 mole of phosphoric acid. We would produce then 1 mole of sodium phosphate and 3 moles of water. Okay, so the chemical reaction helps us bridge that gap between the two. Then, once we have it converted from moles of one substance into moles of the other, then we can use molar conversions to mass, volume, or particles or molecules of it to actually, respond to the questions being asked. Okay, so let's consider a chemical process. Right, so we have titanium oxide with some chlorine gas, some solid carbon, and we're going to produce, looks like titanium 4 chloride and carbon monoxide. So the first thing we need to do is balance this guy out. So we'll help you out with that. do a little balancing and drop in all of our figures here. All right, so it's a 1 to 2 to 2 yielding 1 to 2 ratio for a balanced chemical equation. So then they may ask us about this process: how many moles of chlorine will react with 4.55 moles of carbon? Well, this is a nice one. We like it when they ask us questions in moles because as far as conversion and a balanced chemical equation, we're going to be right in the middle of the diagram. We're going to need to go from moles of 1 in carbon to moles of chlorine gas. Right? So we're starting right in the middle, right between that connecting bridge, or on either side of it. So our setup is quite simple. We start with what we're given, the 4.55 moles of carbon. We should always try to use units at this point in time. I would highly encourage you to make sure or be certain that when you work through your mathematics that you are labeling it in moles of what? Moles of carbon. Because it's easy for you to just write down like 4.55 all by itself and then forget what it is you're starting with and what you're trying to get to. It happens more often than you would think. Students that refuse to write units on numbers and their mathematical work ultimately will make a simple mistake because they'll forget like what the numbers are actually representing. And your final answer must contain units and telling units of what. So we have 4.55 moles of carbon. We need to get out of moles of carbon and get into moles of chlorine. Well, the connecting piece is going to be in the balanced chemical equation. Right? We know how many moles. We know there's 2 moles of carbon for every 2 moles of chlorine gas. Yes, it's a 1-to-1 ratio or a 2-to-2 ratio. Well, we should still just get in the habit of working it into our setup. So moles of carbon on the bottom, moles of chlorine gas, that's what we want to get into on top. It's a 2-to-2 ratio, and so that means it's just simply 4.55 moles of chlorine gas. All right, the follow-up question to that then is what mass of titanium 4 oxide will react with 4.55 moles of carbon? All right, so consider where we're going to be in our diagram. We're going to be starting in moles of carbon. We're given that. And we need to get into mass in grams of titanium oxide. All right, always start with what you're given. 4.55 moles of carbon. What's the next step? And then so what would be the ratio then? What would be the setup? Yeah. Just make sure that the numbers will stick with what it is you're talking about. And that's why the units are easier to put in first and then backtrack and put the numbers in. We need moles of carbon to cancel, as what was mentioned. We need to get into moles of titanium 4 oxide. We can set that up as our conversion fact and then make sure that the numbers that are associated with them from the balanced chemical equation are plugged in too. Okay, that takes care of that. But we're not done yet because they're asking us for mass in grams. So what must be the last factor here? What do we use? We go from moles of something to its mass in grams. Molar mass. Yep, you got it. So what has to be on the bottom? What units would be found on the bottom of our conversion factor here? No. Moles of titanium oxide on the bottom to grams of it on top. Right? We want moles of titanium oxide to cancel. So it needs to go diagonal into the next factor, right? 79.9 grams or so, I think is correct once you round it nearest tenth. That's grams of titanium 4 oxide. And you would be right if you're using the diagram. If dimensional analysis is not your cup of tea, if you don't like setting things up this way, and you're more comfortable with just like looking at the island diagram and knowing what you need to do, then, you multiply by the molar mass. Once you have it in moles of something, you multiply by its molar mass to get it in the grams of it that you might have. So, and it shows that in the setup. Yes, ma'am?
So how did you know it was 1 mole of TiO2 and 2 moles?
From the balanced chemical equation.
Okay.
Yeah, so this is going from moles of the 1 carbon into moles of titanium 4 oxide, and that connecting bridge is our balanced chemical equation. So moles of carbon, it's 2 moles of carbon for every 1 mole of titanium 4 oxide. Yep, good question. And we should find this to be near 182 grams of titanium 4 oxide. Okay, we can move on to another question then, and asking like maybe how many molecules of titanium 4 chloride can be made if we're given 115 grams of titanium 4 oxide. So we're going from a mass in grams to molecules of another component in the process. Right. So if we use our little stoichiometry island diagram, we're going from a mass in grams of titanium 4 oxide into a number of molecules of titanium 4 chloride. So we're going to go from grams to moles of this original component, use the molar ratio from the balanced chemical equation to cross the bridge over to the other mole of titanium 4 chloride, and then convert it from moles into individual particles or molecules of it. So we always start with what we're given, 115 grams of titanium 4 oxide. If we want to go from grams to moles of it, we need to divide by its molar mass. Yep. So grams of titanium 4 oxide needs to go on the bottom, into moles of it on top. Right? Our factor is the molar mass. So for every 1 mole of titanium 4 oxide, there are always 39.9 grams of it. And in this way, grams will cancel. So now we're in moles of titanium 4 oxide. Our next fact is going to come from the balanced chemical equation. And if we hop back into our work from previous week, we would see that's a 1-to-1 ratio. That for every 1 mole of titanium 4 oxide, there will be 1 mole of titanium 4 chloride. Right, and so we run the math through, and we should find that this comes out to near 8.7 times 10 to the 23rd molecules of titanium 4 chloride. So through these several examples, there's a couple things we can pull forward from it. Okay, one, we can make sure that we use coefficients from the equation only when we cross the middle bridge. Right, that's when you're going to make use of that balanced chemical equation. Without that, you cannot cross from one reactant to the other, or one reactant to the product, or product to product. All right, the other 6 bridges always have 1 mole before the substance's formula. Right, we always, when we're trying to cross from grams of it into moles of it, we have 1 mole of it for every so many grams. That's the molar mass. Same thing on the red bridge here, as we go from in moles of titanium 4 chloride to molecules of it. All right, the second thing is the middle bridge conversion factor is the one that has 2 different substances in it. Right, this is where we make the switch from titanium 4 oxide to titanium 4 chloride. That's why it's rather important that we do keep track of what we're working with, especially at this point, because that way you set up the ratio the right way. If you know what you're trying to cancel out of and what you're trying to get into, that it'll help keep the math straight and for you. I think you'll have less opportunity to flip a number accidentally or misplace what you're working with. The conversion factors for the other 6 bridges have the same substance in both numerator and denominator. So only time we change the substance is at the middle bridge. The units on the islands at each end of the bridge being crossed appear in the conversion factor for that bridge. We kind of mentioned the Avogadro's number. Avogadro's number would be what we would go to for molecules. Volume is 22.4 liters per mole, and then grams would be molar mass of the substance. Yep. Okay, so why don't you try this one on? There's a couple of questions here for you. You are given the balanced chemical equation, so that's kind of nice. They're asking you if we had 5.33 times 10 to the 28th molecules of nickel 2 phosphide and have it react with an excess supply of iridium, what mass of iridium 3 would be produced, iridium 3 phosphide. If you would work through that, and then if you have that taken care of, hop into the next question. How many grams of iridium will react with 465 grams of nickel 2 phosphide? Otherwise, I would have you come up on the board and do that, but or at least someone. But all right. So for the first one, we start with what we're given. We're given the number of molecules of the iridium. Or no, sorry, the nickel 2 phosphide. We're going to start with that. We need to convert it into moles of it because we need to eventually cross the molar bridge, I suppose, from one reactant to the other. So we're going to set that up. Avogadro's number on the bottom to 1 mole on top. That cancels away molecules, gets us in the moles of nickel 2 phosphide. Then in the middle conversion term, we need to get out of moles of the nickel 2 phosphide into moles of iridium 3 phosphide. It's a 1 to 2 ratio from the balanced chemical equation. 1 mole of this nickel 2 phosphide to 2 moles of iridium 3 phosphide. So we set that up, cancel away the moles, and we need to then, they want us to know the mass produced, so we're going to multiply by its molar mass, 223.2, and when we punch everything through a calculator, we should end up with like 3.95 times 10 to the 7th grams of iridium 3 phosphide. How many grams of iridium will react with 465 grams of nickel 2 phosphide? We're going to set this up much the same way. We're going to start with our beginning information, 465 grams of our nickel 2 phosphide. And we have 3 conversions to do. The first one, divide by its molar mass. Cancels grams of it into moles of it. Right. The second step is to cross from moles of the nickel 2 phosphide into moles of iridium. It's a 1 to 2 ratio. 1 mole of the nickel 2 phosphide to 2 moles of iridium. And then finally, we need to get into grams of it, grams of iridium. So we're going to need to multiply by its molar mass, 192.2. So 1 mole of iridium, there is 192.2 grams of it. Yeah, 751? Yeah. All right, 632 decimeters, cubic decimeters of butane. You might recall that a cubic decimeter is 1 liter of volume. Bum, bum, bum. Or maybe you don't. But either way, this is a combustion reaction. This is where we're combining a hydrocarbon fuel source with oxygen. And anytime that occurs, if we see anything like this, the result, the products should be, if it's complete combustion, will be carbon dioxide and water. All right, so that's going to be the case anytime you go to burn something in the presence of oxygen. All right, so that sets us up with our generic equation. Now we got to do some balancing, and this one is not an easy one to balance because you actually end up resulting with some large numbers here. You might try to balance out the carbons with a 1 to 4 setup with 4 carbon dioxides to 1 of your butane, and then that means we need to balance out the hydrogens with 5 waters, but that you're going to find that this does not get you what you want. You're still not balanced. So the easiest way to take care of this is to double your butane and then go for balancing, which means you need to double out the carbon dioxide, and you need to bring the number of waters to 10, and that would allow you to say, okay, 13 oxygens will make this work. The problem was 5 waters set you up with an odd number of oxygens, and you have an even number on the left-hand side. So if you run into that problem, an easy solution is try doubling the more exotic molecule, right? Now, another thing to keep in mind is let's say that you don't recognize that this is the stopping point. So you keep going and you increase something. Maybe you go to 4 of these or 3 of these or whatever. Once you have it balanced, you should always check to see if you can reduce it at all to lowest terms. Because if you can reduce the lowest terms, then it'll take you right back to the lowest ratio set you can come up with. Like if we got like 4 to 26 to 16 to 20, we can see that as we can reduce those numbers to lowest terms. We may have missed it the first time around, but we got it even though we overshot a little bit. All right, so don't panic if right away, But if you spend more than 5 minutes trying to balance things, you should probably start over from scratch. Okay, so we have this all set up. Now we need to figure out how many molecules of oxygen react with this. All right, so here's our setup. We're starting with what we're given. We're in decimeters, cubic decimeters. If we recognize that as liters of volume, then we can go right to the our molar conversions. We want to cancel decimeters cubed or liters by dividing by 22.4 for every 1 mole of butane. Then we want to go from moles of butane to moles of oxygen. The balanced chemical equation says 2 moles of butane for every 13 moles of oxygen consumed. And then finally, we need to know the number of molecules. So we're going to use Avogadro's number on top, canceling moles on the bottom. So 1 mole of oxygen will always consist of 6.02 times 10 to the 23rd molecules. All right, so looking at your setup, are you close in your setup? Some people are there. Okay. All right. So, what is your answer then? What did you come up with?
1.10 times 10 to the 26 molecules of oxygen.
Okay. What did you guys get? Same. What did you guys get?
3.8 times 10 to the 26.
Okay. Now, normally when 2 groups agree and your group doesn't, that's not usually a good sign. Yeah, it should be 1.10 times 10 to the 26 molecules of oxygen. Okay, so we're going to talk a little bit about energy in stoichiometry today, and if we can, we'll get to limiting reactants, but I don't know if we're going to get that far. We definitely need to get there before we close up shop. We have a couple labs to do. We also have a penny lab to take care of. Our liquid's been sitting back there in the fume hood for like weeks. I mean, to get to it. Also, your soaps, I tested a couple of them the other day, and they were testing around between 9 and 10 pH, so you should be able to take them home at any point in time. We can bring in some wax paper and some ribbon and time up real fast or something.
That one worksheet we had to do for the penny lab, that's due at the end of the year, right?
Yeah. You don't want to misplace that, because it all gets that put together and turned in all at the same time. Don't get that mystery look on your face.
That might be a part. I'm going to look at my monitor for that real quick. That could easily be this.
That is not going to be good, because you probably have starting data in masses. Yeah.
That might be important.
That could be a problem.
Quote unquote.
All right, but we will, if you need extra copies, I can make some extra copies, but the main thing is the data that you'll be missing. That's the thing. All right, it should be done like on lab paper and yeah. You should have like, I think parts 1 and 2 so far. Okay. I also will be giving you, as we near the end of that project, I will be giving you like a checklist of like what you need to have, and then we can go through and just make sure it gets a rubric like that you have everything. Okay, so let's move forward though. We can take care of that. So I have a housekeeping later on. Not only does the balanced chemical equation tell us the connection between the numbers of moles or grams or liters of gas or whatever are used or produced, but it can also be used to tell us like how much energy is either put into the system or given out by the system in that process, right? For every time through. So if we were to consider like this chemical equation here, this is another combustion reaction. Right? So this is methane being burned in oxygen or with oxygen, and it's producing carbon dioxide and water, but it's also showing us energy given off. So this reaction would be exothermic because it gives energy off as a product. Energy is being lost to the beaker or container or atmosphere around the burning fuel. Right? So that should make sense. Burning of fuel burning natural gas, that gives off heat. So we should expect some energy to be given off overall. Right, so this balanced chemical equation, again, gives us the ratio of moles to moles, but also moles to energy. So we can add like a little energy medallion in our stoichiometry island chain if you wanted to. And so if we're asked how many kilojoules of energy are released when, watch out, when 54 grams of methane are burned, we have the relationship to determine that now. All right, we're starting in grams of methane, and we need to get to energy in kilojoules. And this equation is telling us that for every 1 mole of methane that I burn, I should expect 891 kilojoules each time. So if I double my fuel source, if I have 2 moles of methane, I should get double the energy out. Right? So, and if I used half as much, I would get half as much energy out. Right? So it makes sense. It kind of, I think, flows as we would expect. So how do we set this up? Like any other stoichiometry problem. We start with what we're given, the 54 grams of methane. I know that's low on the board, but just try to bear with us here. And then we need to convert from grams of methane into moles of it, and then from moles of it into energy in kilojoules. Right, so our first setup would be the molar mass of methane, which is 12 from carbon plus 4 from the hydrogens total. That's 16 grams for every 1 mole of methane. So we would divide by the molar mass. If we cancel the units, we end up with just moles of methane. And we need to go from moles of methane to energy. So the connection piece is this. For every 1 mole of methane, because there's not a coefficient there, it's just a coefficient of 1, we would produce 891 kilojoules of energy. We use that as our factor. For every 1 mole of methane, we would produce 891 kilojoules of energy. The units cancel and leave us just with kilojoules. That's what we want. And so then we simply run through the math. Right, we should find this to be around 3,000 kilojoules. So, in this case, we have 2 digits of significance in our given information. So our answer is also only going to have 2 digits of significance in it as well. So if we doubled the mass of the methane we used, then we would expect double the energy because we would be doubling the amount. The number of moles present would be twice as much. Right? So regardless of whether you're looking at it in the unit of the mole or unit of the gram or maybe in liters of gas, it's going to behave much the same way. An increase should result in more energy being given off by this process. We could also use the amount of energy, like if we were told that this process gives off 3,007 kilojoules of energy, they could ask us how many grams of methane have we burned. And we'd work backwards to the process to solve for that. So does that sit okay so far? Makes sense. All right, so let's check out one more example here. So we have the same process. We're burning methane. It tells us that the amount of energy being given out is 891 kilojoules for every time through. And they're asking us what volume of oxygen is consumed in producing 5,430 kilojoules of energy. So we start with that. Right? We're given the energy. We need to get to the volume in liters of oxygen. All right, so we start with our energy, 5,430 kilojoules. We know from the balanced chemical equation that for every 891 kilojoules, there would be 2 moles of oxygen consumed. Right? Because in our balanced chemical equation, it's a 891 kilojoules to 2 moles of oxygen ratio. What goes in our next conversion fact?
44 liters.
Yeah. Would that be on top or the bottom?
Top.
Yeah. Absolutely correct. Yeah, we want to go from moles of oxygen gas that we're in now and get into liters of oxygen gas, so we use the molar volume to convert. Yep, absolutely true. And now it's just a matter of, again, punching it through our calculator. And so we can save you a little bit of time and cut right to the chase as we 273 liters of oxygen. All right, so here's what I'd like to do to kind of close out today. The last question is asking you, I think, how many grams of water?
What is the mass?
Oh, yeah, the grams of water made if so much energy is released. If you would, take a moment and try to solve for that. Right? You should be able to solve this problem in the next 5 minutes. All right, so hopefully your setup is very similar to what we have up here. You're going to start with the energy given. You need to convert from the energy into moles of water. And we know that relationship is 891 kilojoules for every 2 moles of water that are produced. And then we need to go from moles of water into grams of it. So we're going to multiply by water's molar mass, 18 grams per mole. What do you come up with?
426.
Yeah, it should be around 426 or so, I believe. Yeah, we'll hit the forward thing. Yeah. Yeah, so 426 grams of water. Okay, so the balanced equation for making a Big Mac might be 3 buns, 2 meats, plus everything else. And so our formula for a Big Mac would be B3M2EE, or E2, I suppose, if we wanted to combine it, right? But it's everything else. It's like meaning one thing. So if we had 30 meats, right, and we have an unlimited supply of buns, an unlimited supply of everything else, how many of these Big Macs can we make? 15. 15. 0.0. 15.0. Right? If we had 30 buns, an unlimited supply of meats, and everything else, we could make...
16.
No. If you're not going to be helpful, then just don't say anything. All right, 10.0. Right, 10.0. Remember, when these run out, we can no longer make any more Big Macs. So if it takes 3 buns, and we have 30, we can only make 10 with a limitless supply of everything else. But what if we had 30 meats and 30 buns and lots of extra everything else? We could still only can make 10. Right? Why is this? Because we're limited by one of the reactants. Shocker. So, like if we then look at a chemical process, it's the same way. When you run out of one of the reactants, you're done. You cannot make any more. You are done. Game over. Thanks for playing. Get them next time. All right, so you could use for really anything you have to assemble different parts to make one object with. Similar kind of process happens in chemistry. We take a couple of different components, reactants. We break the bonds that make them what they are. We spread them out a little bit. We let them rearrange and reorganize into something different at the end. And so if we happen to have a formula for a tricycle, so we need 3 wheels, we need 2 pedals, we need a seat, we need a handlebar, and we need a frame. Right, so if we add that all together, that's W3P2SHF. Okay, so if we had 50 pedals and a limitless supply of everything else, we could make a total of 25. If we had 50 seats and everything else was a limitless supply, we could make 50 of these darn tricycles. Right? If we had 50 pedals, 50 seats, and unlimited supply of anything else, we still can only make 25, even though we have extra seats to go around, because the pedals are limiting us. We're out of pedals. We can no longer make any tricycles. And you could try to sell them, but the manager might think we're crazy, but we're going to sell you this tricycle at 25% off because it's missing the pedals. It's a steal. It's a steal. All right, so that's kind of silly analogies for limiting reactants. But if we push it into an actual chemical process like such, right? We have solid aluminum reacting with chlorine gas. So Al solid with chlorine gas, Cl2G. And we're going to produce a solid aluminum chloride. We balance this guy up. It's already given to us a balanced. We should be able to respond to the following questions. If 125 grams of aluminum react with an unlimited supply of chlorine, how many grams of aluminum chloride are made? And then we could flip it around the other way around. We could run it with, if we had 125 grams of chlorine reacting with an unlimited amount of aluminum, how much would we make? And so we could compare. We could run them through. All right, so we simply set these up just like we would any other stoichiometry problem. They look very similar to the things we were working with between yesterday and today. And we simply set things up with what we're given. So 125 grams of aluminum. We're going to do conversions. We have to go from mass to moles of the other to mass of the other. So we need 3 conversions here. All right, the molar mass of aluminum, 27 grams for every mole of it. The balanced chemical equation says it's a 2 mole to 2 mole ratio between aluminum used and aluminum chloride made. And then finally, to get into mass of the aluminum chloride, we need its molar mass. So for every 1 mole of aluminum chloride, there are 133.5 grams of aluminum chloride. So we write this all down. We we ship it down to the monkeys downstairs that are computing things for us, and they spit out a result of 618 grams of aluminum chloride. Okay, we're going to do the same process for the other question, but instead we're working from the opposite direction as far as like the reactant. So we're working with chlorine to aluminum chloride. So we do 125 grams of chlorine gas. The molar mass of chlorine gas is 71 grams per mole. So we put 71 grams on the bottom to 1 mole of Cl2 on top. We use the balanced chemical equation to find the molar ratio between chlorine gas and aluminum chloride. It's a 3 to 2 step or ratio. And then finally, the molar mass of aluminum chloride, which is 133.5 for every mole of it. All right, and we find that we can actually make with the 125 grams of chlorine gas, we can only make 157 grams of the aluminum chloride. If we were to be asked a question, if 125 grams of aluminum reacts with 125 grams of chlorine, how many grams of aluminum chloride are made? We'd have to go with the lesser amount, right? The 157 grams of aluminum chloride. Why? Because we're out of chlorine gas. At that point, we're out, and the process would be done. Our previous answers were based upon the understanding that we had an unlimited supply of the other reactant, right? And so if we put in the situation that we're limited in grams of mass for each of the reactants, then we have to decide which one will end up being used up first, which will produce, I guess, the lowest yield because of how much is used each time through the process. So this is known as that limiting reactant. It's the reactant that runs out first. It's going to be based, the amount of product is based on the limiting reactant. So once you know what the limiting reactant is, any other calculations that you make will have to be used or branched from that limiting amount. The one that does not run out then would be the excess reactant, right? Like in a root beer float, the limiting reactant is usually the ice cream. Usually the ice cream's gone, you still have root beer left. Usually. And you plop some more ice cream in there and eat it. Right? What's the product here, though? And the product? Your enjoyment. Your enjoyment. So when you run out of the ice cream, put more ice cream in there? Oh, all right. It's good. We're good. It's great. Okay, we're almost done. Kinda. All right, so we from our previous examples, we can pull from information and identify what the limiting reactant is. With 30 pieces of meat and 30 buns and a limited amount of everything else, we found that we can make only 10 Big Macs. The limiting reactant then was the number of buns. It shut us down when we ran out. The excess reactant would be the meats and everything else. We'd still have patties left over. We'd still have everything else left over from the process. Not everything would have been used up. With the bicycle example, we had 50 pedals and 50 seats and unlimited of everything else. What limited us to only 25 tricycles? It had to be the pedals. We ran out. We'd still have some seats left over. We'd still have all the other components, the wheels and the seat and the handlebar and the frame. For our example in a chemical process, with 125 grams of aluminum and 125 grams of chlorine gas, we found that we could make at most 157 grams of aluminum chloride. So what we said that the chlorine gas limited us, and we'd have leftover aluminum still remaining.